Take a deep breath and allow your body to settle into the stillness of your bed. As you exhale, imagine the air around you cooling and thickening, transforming into the gentle, supportive weight of tropical seawater. We are descending now, not into darkness, but into a world of liquid twilight off the coast of Queensland, Australia. Beneath us lies the Great Barrier Reef, the largest living structure on Earth, stretching over 2,300 kilometers in a vibrant ribbon of life. It is a few nights after the full moon in November, and the ocean is waiting for a miracle. What most people don't realize is that for 364 days a year, the reef is a place of slow, stony growth, but tonight, it will transform into a theater of underwater snowfall. This is the mass coral spawning, an event so synchronized and so vast that it can be seen from the reaches of space, yet it begins with a single, microscopic chemical signal. As you drift in this warm, saline embrace, notice the temperature of the water. It is exactly 27 degrees Celsius, about 81 degrees Fahrenheit. This is no coincidence. For the corals to release their life into the current, the water must reach this specific thermal threshold, sustained for several weeks leading up to the event. You can feel that warmth against your skin, a velvet pressure that makes you feel entirely weightless. The reef below is not a silent place. If you listen closely, past the rhythmic pulse of your own breathing, you can hear the muffled, high-frequency crackling of snapping shrimp, a sound often compared to the sizzling of 1,000 tiny campfires. Look closely at the structures beneath you. You are hovering over a garden of acropora corals, commonly known as staghorn and elkhorn corals. These are the master architects of the reef. Here is a fascinating biological reality. While they look like jagged stone, these corals are actually colonies of thousands of tiny, soft-bodied animals called polyps. Each polyp is housed in a tiny cup of calcium carbonate, which the coral secretes at a rate of only about 1 to 10 centimeters per year. To your touch, the living surface of the coral would feel slightly slimy or gelatinous. This is a protective layer of mucus that keeps the polyps hydrated and wards off debris. What is happening right now is a feat of celestial engineering. Within the translucent tissues of these polyps, tiny biological clocks are ticking. Corals possess primitive eyes in the form of blue light sensing proteins called cryptochromes. These proteins allow the coral to detect the exact moment the moon rises and the intensity of its glow. Here's something truly incredible. The spawning won't happen until the moon has risen high enough to signal the ebb of the tide, ensuring the water is calm enough for the next generation to find a home. As you watch, you'll notice a change in the polyps. They are setting. This is a term marine biologists use to describe the moment the colorful gamete bundles, containing both eggs and sperm, become visible in the mouths of the polyps. They look like tiny translucent pearls. In the species Acropora millipora, these bundles are a vibrant dusty rose or a soft peach color. They are small, usually only 2 to 3 millimeters in diameter, roughly the size of a peppercorn. The anticipation in the water is palpable. The reef uses chemical messengers called pheromones to communicate across the current. Even though these organisms are miles apart, they are whispering to one another through the chemistry of the sea, ensuring that over 130 different species of coral will release their bundles within the same 20 to 30-minute window. It is a moment of perfect, quiet unity. Suddenly, the first release begins. A single colony of brain coral, or Diploria labyrinthiformis, releases its bundles. They don't sink, they rise. Because these bundles are rich in lipids, fats that are lighter than seawater, They begin a slow, graceful ascent toward the surface. It looks like a snowstorm in reverse. Imagine millions of tiny glowing spheres of pink, orange, and white, drifting upward through the dark blue water column. The scale of this is hard to comprehend. A single large coral colony can release tens of thousands of these bundles. As you float among them, you are surrounded by billions of potential lives. The water around you is no longer just clear liquid. It has become a thick, nutritious soup of biological potential. This event is so massive that the smell of the ocean changes. If you were at the surface, you would smell a sweet, earthy scent. This is caused by the release of dimethyl sulfide, or DMS, a gas produced by the coral's symbiotic algae. It is the very scent of life itself, a fragrant signal that the reef is renewing. Notice the texture of the snow as it brushes past you. It is soft, buoyant, and gentle. There is no urgency here, only the steady upward pull of the tide. What's fascinating is the role of the zooxanthellae. These are microscopic single-celled algae that live inside the coral polyps. They provide up to 90% of the coral's energy through photosynthesis during the day. During the spawning, some corals actually pack a lunch for their offspring, passing on a supply of these algae into the gamete bundles so the new larvae will have a source of energy as they drift. As the snowfall intensifies, the water becomes a kaleidoscope. You might see the Favetes corals, often called honeycomb corals, releasing their bundles in a slightly different shade of pale yellow. The reef is a mosaic of architecture, from the delicate branching structures that look like underwater forests to the massive rounded boulders of Poritz corals, some of which are over 500 years old. These ancient giants have participated in this dance 5 centuries over, witnessing the slow shift of the tides and the turn of the stars. The sound of the reef changes during the spawning. The usual nighttime activity of the fish slows down, as if the entire ecosystem is holding its breath. The water feels thicker, more viscous, as the concentration of organic material increases. This is the photic zone, the upper 15 meters of the ocean where light can penetrate. Even though it is night, the faint luminescence of dinoflagellates, tiny plankton that glow when moved, creates a shimmering trail behind every rising bundle. It is as if the water is filled with living stars. Consider the journey of a single bundle. It must rise through the water column, avoiding the gentle filter feeders that call the reef home. Once it reaches the surface, the bundle will break apart, allowing the eggs and sperm to mingle with those from other colonies. This is a critical moment for genetic diversity. The ocean surface becomes a vast, swirling nursery, a slick of pink and red that can stretch for several kilometers. The sheer mathematics of the event is staggering. If you were to count the number of eggs released on a single hectare of reef, the number would reach into the trillions. Yet, each one is governed by the same simple laws of buoyancy and chemistry. The larvae that form, called planulae, are tiny pear-shaped organisms covered in microscopic hair-like structures called cilia. These cilia act like tiny oars, allowing the larvae to swim, not against the current, but enough to navigate toward a suitable place to land. As you drift in this underwater blizzard, feel the immense peace of a process that has remained unchanged for millions of years. The coral reefs cover less than 1% of the seafloor, yet they are the nursery for a quarter of all marine life. Tonight, you are witnessing the engine of that life. The water is a protective blanket, a warm, salt-scented womb that cradles the future of the ocean. You might notice the way your body feels in this simulated sea. limbs heavy, yet supported, your heart rate slowing to match the rhythmic surge of the swells above. The ocean is a master of patience. It does not hurry the coral. It waits for the moon, waits for the temperature, waits for the tide. There is a profound lesson in this stillness. Everything happens in its own time. The snow continues to rise, a silent upward rain of peach and cream. Each bundle carries the blueprint for a new reef, a new colony that might one day grow to be the size of a house. But for now, they are just tiny specks of light in a vast dark sea. The water feels increasingly soft, the salt minerals in the ocean acting like a balm on your skin. What's truly remarkable is that this event was only first discovered by scientists in 1981. For thousands of years, it happened in total secret, a private celebration of the natural world. It reminds us that there are still mysteries in the deep, quiet places of the world, processes of growth and renewal that require nothing from us but our silent observation. As the first phase of our journey through the spawning concludes, feel yourself sinking deeper into the soft sand of your imagination. The snowfall is at its peak now, a thick, beautiful haze of life. You are safe, you are weightless, and you are part of this ancient rhythmic cycle. The reef is breathing, the moon is watching, and the ocean is full of stars. We will continue to drift here, watching the microscopic wonders of the deep as they begin their long, slow journey toward the light of the surface. In the silence of the underwater night, everything is exactly as it should be. The water is warm, the current is kind, and the reef is reborn. As the thousands of rosy gamete bundles continue their slow, buoyant journey toward the surface, picture the ocean not just as a body of water, but as a vast saline library, holding the records of millions of years of biological memory. While you float in this suspension of life, it is worth considering how recently the human world actually came to understand this phenomenon. For the longest time, the scientific community believed that most corals reproduced by brooding, releasing fully formed larvae into the water one by one. It wasn't until a humid night in October 1981 that the truth was revealed. 3 PhD students from James Cook University, Peter Harrison, Russ Babcock, and Oliver Willis, were diving on the central Great Barrier Reef when they became the first Western scientists to document this synchronized mass spawning. Imagine their surprise as the world around them suddenly filled with what they described as an underwater snowstorm. Before this moment, this massive coordinated pulse of life was completely unknown to modern marine biology. However, what is particularly compelling is that while Western science was late to the party, the indigenous peoples of the Australian coast, such as the Gungandji and Mandubara clans, have held this knowledge for tens of thousands of years. They recognized the red water, or the sea turning to wine, as a vital marker in their seasonal calendars, a sign of the reef's rejuvenation. At this very moment, you are observing a process that consumes an immense amount of the coral's vitality. A single colony of Acropora, the branching corals that look like the antlers of a stag, will dedicate up to 50% of its annual energy budget to this one night. To put that in perspective, the coral spends half of all the sunlight it has captured through its symbiotic algae over the last 365 days, just to create these tiny lipid-rich spheres. These lipids, or fats, are what give the bundles their buoyancy. Because oil is less dense than water, the bundles rise at a steady rate of approximately 1 to 2 meters per minute. Notice how the water feels as it carries these travelers. The sea is exceptionally calm tonight because the spawning almost always occurs during a neap tide, a period when the difference between high and low tide is at its smallest. This lack of turbulence is essential. If the water were too choppy, the gamete bundles would be dispersed too quickly, preventing them from finding their counterparts at the surface. Scientists have observed that the spawning typically waits until 4 to 6 nights after the full moon, once the moon has risen high enough to signal the turn of the tide. This celestial synchronization ensures that the billions of eggs and sperm meet in a concentrated slick at the surface, rather than being swept out into the deep, inhospitable trenches of the coral sea. Consider the history contained in the very skeletons beneath you. Some of the massive boulder corals you see, the porites species, can grow to be over 8 meters in height and live for more than 500 years. This means some of the individuals participating in the spawning tonight were already established on this reef when Captain James Cook first sailed the Endeavour through these waters in 1770. In his journals, Cook and his naturalist Joseph Banks described seeing long streaks of sea sawdust on the surface. For centuries, mariners assumed this was just floating debris or blooms of a cyanobacterium called trichodesmium. It is now understood that many of those historical sightings were likely the aftermath of a massive coral spawning. The visible signature of a reef in the midst of its most intimate act of creation. What's happening now is a transformation of chemistry. As the bundles reach the air-water interface, the surface tension of the ocean causes them to pop and break apart. This is the moment of fertilization. The eggs, which are about 0.5 millimeters in diameter, are now free to meet the sperm from other colonies. This isn't just a random scramble. It is a masterclass in genetic diversity. By timing their release so precisely, different colonies of the same species ensure they are cross-fertilizing, which strengthens the resilience of the entire reef system. Within about 24 to 48 hours of this moment, these fertilized eggs will develop into planulae, tiny pear-shaped larvae. Each planula is roughly 1 millimeter long and is covered in thousands of microscopic hair-like structures called cilia. If you could see them under a magnifying glass, you would notice these cilia beating in a rhythmic wave-like pattern, allowing the larvae to propel themselves through the water. While they are still at the mercy of the major currents, they are not entirely helpless. They are active explorers. Deep within their tiny bodies, these larvae possess an extraordinary sensory kit. They can smell the reef. This biological phenomenon, known as chemoreception, allows the larvae to detect chemical signals released by specific types of algae. In particular, they are searching for crustose coralline algae, or CCA. This is a hard, pinkish crust that grows on the rocks of the reef. To a coral larva, the scent of CCA is a signal that the location is a healthy, stable place to anchor. Without this specific chemical smell, the larva will continue to drift, searching for the perfect home. Furthermore, these tiny travelers are listening. It was recently discovered that coral larvae are attracted to the sounds of a vibrant reef, the low-frequency grunts of fish, and the high-frequency snaps of shrimp. They swim toward the noise, using the acoustic landscape of the ocean as a compass. It's a beautiful thought. These microscopic specks of life are navigating through a dark, vast ocean by listening for the music of their future home. As you hover in this liquid space, feel the profound age of this process. Scleractinian corals, the type that build these massive reefs, have been part of the Earth's oceans for nearly 500 million years. They have survived 5 major mass extinctions, including the one that claimed the dinosaurs. The mechanism you are witnessing, the extraction of calcium carbonate from seawater to build aragonite skeletons, is one of the most successful engineering feats in the history of life. Every year, the Great Barrier Reef produces billions of tons of this limestone, creating a structure so large it covers 344,400 square kilometers, an area larger than the United Kingdom, Switzerland, and the Netherlands combined. The texture of the water around you is changing slightly as the night progresses. The concentration of organic material from the spawning creates a slight viscosity, a feeling of being enveloped in a nutrient-rich broth. This organic rain provides a massive surge of food for the entire ecosystem. Even the corals themselves will feed on the excess nutrients, though they are careful not to consume their own kind. It is a closed-loop system of incredible efficiency. Take a moment to visualize the surface of the water from below. It looks like a shimmering silver mirror, but it is currently coated in a thick, pinkish quilt of life. This slick can be several centimeters deep and stretch for many kilometers. Here, under the warmth of the tropical sun that will rise in a few hours, the embryos will begin the rapid process of cell division. They will go from a single cell to 2, then 4, then 8, in a sequence that has remained virtually unchanged for eons. What is happening now is a silent, microscopic miracle. Of the millions of eggs released by a single colony tonight, the survival rate is dauntingly low. Statistically, only about 1 in a million coral eggs will survive to become a reproductive adult. Many will be swept into the open ocean where the water is too deep for them to settle. Others will simply run out of energy before they find a suitable substrate. Yet, because the scale of the spawning is so massive, involving over 130 different species across the reef, even those slim odds are enough to ensure the reef's survival. The water remains at a steady, comforting 27 degrees Celsius. This temperature is vital for the metabolic processes of the developing larvae. If the water were just a few degrees cooler, their development would slow down, leaving them vulnerable in the planktonic stage for longer. The reef knows this. It has waited for the perfect thermal window, the perfect lunar phase, and the perfect tidal lull. As you drift, notice the way the light from the moon penetrates the upper layers of the water. It creates long, dancing shafts of pale blue that illuminate the rising snow. There is no sound here, but the rhythmic low-frequency thrum of the ocean itself, a sound that has been called the heartbeat of the world. You are a witness to the most significant night of the year for the largest living organism on the planet. The reef is not a static object. It is a slow-motion explosion of life. Every branch of staghorn, every mound of brain coral, and every delicate fan of sea whip is a result of a night just like this one, occurring year after year, century after century. The continuity is breathtaking. You are part of this timeline now, a silent observer in a sequence of events that stretches back to the dawn of complex life. Feel the weightlessness of your body as it mimics the buoyancy of the coral spawn. There is no effort required. Like the larvae, you are simply being carried by the gentle, persistent rhythms of the sea. The water is a cradle, the reef is a nursery, and the night is a long, slow breath of renewal. In this deep, saline quiet, the future of the ocean is being written, one tiny rising pearl at a time. The upward journey of the coral spawn continues, a slow-motion ballet that transforms the darkened sea into a living snow globe. If you were to reach out and touch the water now, it would feel slightly thicker, almost like a thin syrup, due to the sheer concentration of organic material being released. This phenomenon is a masterpiece of timing, but to truly understand the scale of what is happening, think of each individual coral colony as a high-density city. Within a single square meter of a healthy reef, There can be over 10,000 individual coral polyps. Each one of these polyps is roughly the size of a pinhead, yet they work in absolute concert. What's occurring at the surface now is a process scientists call fragmentation and fusion. As the gamete bundles reach the surface, they encounter the air-water interface, where the surface tension causes them to rupture. Picture a tiny balloon, no larger than a peppercorn, filled with even smaller spheres of oil and life. When these balloons pop, they release the eggs and sperm into a two-dimensional plane. This is essential for the survival of the species. In the three-dimensional volume of the ocean, the chances of an egg meeting a sperm are slim. But by concentrating them on the flat surface of the sea, the reef effectively turns a vast void into a crowded ballroom. Observe the way these slicks begin to form. To the human eye, from a boat or a plane, they look like long, winding paths of reddish-brown or pink dust scattered across the water. Scientists using the MODIS instrument on NASA's Terra and Aqua satellites have actually been able to track these slicks from orbit. Imagine that. An event involving creatures the size of a grain of salt creates a visual signature so large it can be monitored from 700 kilometers above the Earth. It is as if the reef is painting its own history across the surface of the planet. Within these slicks, a chemical key and lock system is at work. Every species of coral, such as the delicate Montipora or the sturdy Turbinaria, releases specific proteins and peptides that act like a biological signature. An egg from a Favites coral will only accept sperm from its own species. Think of it like a specialized postal service, where every letter has a unique code that only one specific mailbox can open. This prevents crossbreeding between different types of coral and ensures that the genetic integrity of each species is maintained, even when billions of gametes are swirling together in the same current. As you float here, consider the life of a single planula, the larva that forms once fertilization is successful. Within about 24 to 48 hours, these embryos develop into tiny pear-shaped organisms. They are roughly 1 millimeter long, about the same size as a single grain of coarse salt you might sprinkle on your dinner. At this very moment, these planulae are becoming active swimmers. They are covered in thousands of cilia, which are microscopic hair-like structures that beat in a coordinated rhythm. To a planula, the water doesn't feel like a liquid. Because of their tiny size, the water feels more like a thick gel or even a soft solid. They have to work hard to move through it, using their cilia like thousands of tiny oars to navigate the currents. Something that often surprises people is the lunchbox these larvae carry. Many species of coral, particularly the acropora that dominate the Great Barrier Reef, perform what is known as vertical transmission. This means the mother colony actually packages a starter kit of symbiotic algae, specifically Symbiodiniaceae, into the egg. These algae are like living solar panels. They will provide the growing larva with energy through photosynthesis, allowing the tiny creature to survive for weeks in the open ocean without needing to find its own food. It is the ultimate survival pack, a gift of energy from the parent to the offspring. Think of the journey these larvae are about to undertake. Driven by the southward flowing East Australian current, these tiny travelers can cover distances of over 100 kilometers in just a few days. They are the explorers of the sea, searching for a new territory to claim. But they aren't just drifting aimlessly. They are incredibly discerning. As they get closer to a potential home, they begin to use their sensory organs. Notice how the environment smells to a larva. They are searching for the scent of crustose coralline algae, or CCA. This is a hard, pinkish crust that grows on the limestone of the reef. To a coral larva, the scent of CCA is like the smell of a home-cooked meal or a familiar fireplace. It tells them that the rock is clean, stable, and ready for a new tenant. Scientists have found that the larvae can detect even minute concentrations of chemicals, like fluoridoside, which is produced by these algae. If they don't smell that specific chemical, they will keep swimming, sometimes for up to 30 days, until they find the perfect landing strip. At this very moment, the sea is also full of sound. While it might seem silent to us, the reef is a noisy metropolis. Fish like the damselfish and the parrotfish make low-frequency grunts and scrapes, and the snapping shrimp create a constant, high-frequency crackle. Think of this sound as a lighthouse for the larvae. Because sound travels 4 times faster in water than in air, it provides a reliable map. The planulae actually swim toward the noise of a healthy reef, using the music of the ecosystem to guide them back toward the safety of the shallow waters. Consider the physical construction that follows. Once a larva finds a piece of CCA, it undergoes a radical transformation called metamorphosis. It flattens itself out into a disc and begins to secrete a tiny skeleton of calcium carbonate. This is the first brick in a structure that might eventually weigh several tons. To build this skeleton, the coral must extract calcium and carbonate ions from the surrounding seawater. This is a slow, methodical process. A branching coral might grow about 10 to 20 centimeters a year, roughly the speed at which your own fingernails grow. A massive boulder coral, like the porites, grows much slower, adding only about 5 to 10 millimeters of height every 12 months. This is the pace of the reef, a steady, patient accumulation of stone and life. Picture this growth in terms of a human city. If a coral polyp were the size of a person, a large reef structure would be taller than the Burj Khalifa and wider than the City of London. And yet, this entire metropolis is built by tiny, soft-bodied animals, using nothing but the minerals dissolved in the water and the energy of the sun. It is an engineering marvel that puts our own steel and concrete to shame. As you observe the snowfall thinning out, the first phase of the spawning begins to settle into its next chapter. The water temperature remains a steady, comforting 27 degrees Celsius, which is the optimal temperature for the enzymes in the developing larvae to function. If the water were to drop even 2 degrees, the metabolic rate of these tiny creatures would fall by nearly half, making them sluggish and less likely to find a home. The reef's timing is not just beautiful, it is a thermal necessity. The sense of interconnection here is profound. The spawning isn't just about the coral, it's a banquet for the entire ocean. While we avoid the thought of predators, we can observe the way the nutrients from the unfertilized eggs are absorbed by the water itself. This organic rain provides a massive surge of nitrogen and phosphorus to the surrounding waters, fueling the growth of phytoplankton. These microscopic plants, in turn, produce about 50 to 80% of the Earth's oxygen. So, in a very real way, the breath you are taking right now, as you lie in your bed, is connected to the coral spawning happening thousands of miles away. The reef is a vital organ in the body of the planet, and tonight is its most important heartbeat. Take a moment to feel the weight of your own body, mirroring the slow settlement of the larvae. Just as they are searching for a stable place to anchor and grow, you are finding your own place of rest. There is no need to hurry. The reef doesn't grow in a day, and the ocean doesn't empty in a tide. Everything is governed by these long, slow timescales. As the lunar light shifts, moving across the surface of the ripples, the sea sawdust continues to swirl in the currents. Each streak of pink on the surface is a promise of future growth, a testament to the resilience of life. The history of the reef is written in these layers of calcium carbonate, a record of thousands of years of nights just like this one. You are floating in a moment of pure potential, a time when the boundaries between individual organisms blur and the entire ocean becomes a single unified cradle of life. The water around you is calm, the neap tide ensuring that the surface remains as smooth as a mirror. In this stillness, the chemical and acoustic signals are clear. The larvae are swimming, the algae are providing energy, and the foundations of the future are being laid. In the deep, quiet world of the reef, the work of renewal is peaceful, methodical, and certain. You can feel that certainty in the steady pulse of the waves and the warmth of the tropical sea. Everything is in its place. And the great underwater snowfall continues its quiet, miraculous journey. As the millions of microscopic travelers continue their slow, rhythmic dispersal across the surface of the coral sea, it is helpful to shift our perspective from the immediate flurry of the night to the immense, patient timescales of the reef's history. At this very moment, beneath the shimmering pink slicks, a silent and ancient chemistry is at work, a process that connects the very cells of these tiny coral larvae to the structural integrity of our own lives. Consider the composition of the reef itself. The jagged, sturdy structures you hover over are made of aragonite, a specific crystalline form of calcium carbonate. What is truly compelling is that the same calcium being pulled from the seawater to build these underwater cathedrals is the same element that gives strength to your own bones as you lie still tonight. There is a deep biological kinship between the skeletal architecture of the scleractinia, the hard corals, and your own physical frame. As you feel the weight of your limbs sinking into your mattress, you are experiencing the same gravitational pull that will eventually draw these coral larvae back down from the surface to anchor themselves to the stone. Scientists discovered that corals utilize a specialized enzyme called carbonic anhydrase to accelerate this calcification process. This enzyme allows the coral polyps to convert bicarbonate from the ocean water into solid limestone at a rate much faster than would occur through simple chemistry alone. It is a slow, methodical construction project. A massive colony of porites, often referred to as a boulder coral, might only add about 1 centimeter of height to its structure each year. If you look at one of these ancient giants, some of which are over 8 meters tall, you are looking at a living entity that has been steadily building itself for over 800 years. Picture this. These massive corals contain internal growth bands, much like the rings of a tree. By drilling small, harmless cores into these colonies, researchers can read the history of the ocean like a book. These bands provide an oxygen isotope ratio that acts as a natural thermometer, allowing us to reconstruct the sea temperatures and rainfall patterns of the 16th century. Each night of spawning you've observed is recorded in these layers of stone, a silent archive of the Earth's climatic heartbeat. The reef is not just a habitat, it is a library made of calcium. Notice how the water around you acts as a protective shield. Beyond the biological beauty, the reef serves a critical physical function for the planet. A healthy coral reef can buffer up to 97% of the energy from incoming waves. This means that during heavy swells, the intricate branching structures of the acropora and the dense mounds of the brain corals act as a massive, submerged breakwater, protecting thousands of miles of tropical shorelines from erosion. It is a soft-bodied animal, creating a fortress that protects entire continents. What's happening now in the life cycle of the larvae is a shift in their internal compass. Initially, when the gamete bundles were released, the larvae were negatively geotactic. This is a scientific way of saying they were biologically programmed to swim away from the pull of gravity, seeking the light and warmth of the surface. But as the hours pass and they mature into planulae, their internal chemistry shifts. They become positively geotactic. They begin to feel the gentle, persistent tug of the seafloor once again. Imagine this transition as a slow, graceful descent, a return to the foundations. Each planula is now searching for a very specific type of neighborhood. Scientists have observed that these larvae are incredibly picky about where they settle. They are looking for a substrate that is not only stable, but also seasoned, with a specific pink crust called crustose coralline algae. This algae acts as a biological primer, preparing the bare rock for the coral. Without this pink crust, the larva may refuse to land, continuing its journey for days or even weeks. It is looking for the scent of a healthy home, a chemical signal that says, this is a place where life can thrive. Consider the sheer productivity of this environment, a phenomenon often called Darwin's paradox. Tropical oceans are typically nutrient deserts, meaning the water is crystal clear because it contains very little dissolved food. Yet the coral reef is a lush, teeming metropolis of life. The secret lies in the recycling. The coral polyps and their symbiotic algae, the zooxanthellae, are masters of efficiency. They pass nutrients back and forth in a closed loop, ensuring that almost nothing is wasted. A single square centimeter of coral tissue can harbor over 1 million of these tiny algae cells. They are like millions of tiny green suns living inside the coral's skin, providing the energy required to build the limestone world. As you breathe in the cool, still air of your room, think about the global biological pump. The reef doesn't just build stone, it sequesters carbon. By pulling carbon dioxide from the water to create calcium carbonate, the reef helps regulate the chemistry of the entire ocean. It is a vital organ in the Earth's respiratory system. The scale of this is immense. The Great Barrier Reef alone is composed of approximately 3,000 individual reefs and 900 islands, creating a mosaic of life that covers an area larger than the state of Italy. At this very moment, the larvae are also utilizing a sense we are only beginning to understand: underwater hearing. Research has shown that coral larvae will swim toward the sound of a healthy reef. To a tiny planula, the reef sounds like a crackling, thrumming festival. The snaps of the alphidae, the snapping shrimp, and the low-frequency grunts and chirps of territorial damselfish act as an acoustic homing beacon. It's a beautiful thought. These microscopic, sightless creatures are navigating through miles of dark, open ocean by listening for the music of their ancestors. The personal connection here is one of shared rhythm. Much like the reef waits for the moon, your body waits for the night to perform its own essential work of repair and renewal. While you rest, your brain is performing its own version of a mass spawning, a surge of restorative processes that clear cellular debris and strengthen the neural connections you've built during the day. The same patience required for a coral larva to find its home is the patience your body uses to drift toward sleep. Picture the skeleton of a single polyp, called a corallite. It is a delicate star-shaped cup made of aragonite needles. When the polyp is disturbed or when the sun is too bright, it retracts into this cup for protection. It is a perfect custom-made sanctuary. As you settle deeper into your own sanctuary of sheets and pillows, imagine yourself as supported and protected as a polyp in its corallite. The reef provides a home for 25% of all marine species, yet it covers less than 1% of the ocean floor. It is a testament to what can be achieved when life works in total cooperation. Notice the temperature of the water again, that steady velvet 27 degrees Celsius. This warmth is the engine of the spawning. It influences the viscosity of the water, making it just thin enough for the larvae to swim using their cilia, which are like thousands of microscopic beating hairs. If you could see a planula up close, it would look like a tiny glowing pear, moving with a rotating spiral motion. This spiral movement is one of the most ancient forms of locomotion on our planet, a design that has remained effective for over 500 million years. What's fascinating is the longevity of the genetic material. Because corals can reproduce both sexually during this spawning and asexually by budding and cloning themselves, a single genetic individual can technically live for thousands of years. When a piece of coral breaks off and starts a new colony, it is a perfect clone of the parent. This means that some of the coral individuals you are looking at tonight may have been alive, in one form or another, since the end of the last ice age. They are the true elders of our world, silent witnesses to the slow rise and fall of the seas. As the night moves toward the early hours of the morning, the mass of spawn at the surface begins to thin. The fertilization has been successful. The trillions of individual cells are now embryos, beginning the rapid silent process of division. They are no longer just potential. They are the architects of the future. The ocean feels vast, but in this moment, it is also incredibly intimate. Every gallon of water is filled with the promise of new life, a testament to the fact that even the smallest organisms can build the largest structures on Earth. Feel the stillness of the water as the neap tide reaches its peak. The surface is as smooth as glass, reflecting the stars above. The underwater snowfall has transitioned into a quiet, downward rain of larvae, each one a tiny voyager seeking a place to belong. There is no urgency in their descent. They are carried by the same ancient, reliable laws of physics and biology that govern the stars and the tides. You are part of this equilibrium. In the quiet theater of the reef, everything is unfolding exactly as it has for eons, slowly, purposefully, and with a beauty that requires no audience. The reef is growing, the larvae are landing, and the ocean is at peace. As the pink and peach-colored slicks of the coral spawn continue to swirl on the surface of the Australian Sea, let's explore the intricate mechanics, the invisible biological gears that drive this massive synchronization. Scientists have discovered that corals are not merely passive residents of the reef. They are sophisticated light sensors. Within the translucent tissues of a coral polyp, there are proteins called cryptochromes. These are ancient blue light-sensitive molecules that exist in many living things, including us. In corals, these proteins act like a biological stopwatch, measuring the exact intensity and duration of moonlight to ensure that every colony on the reef, from the branching acropora to the massive favia, releases its life-giving bundles at the same precise hour. What is biologically astounding is how these creatures, which lack a central nervous system, manage to communicate across the vastness of the current. They utilize a system of chemical signaling called pheromones. Imagine the water around you is not just a liquid, but a medium for a complex, invisible conversation. As the first corals begin to spawn, they release these chemical messengers into the sea. When neighboring corals detect these molecules through their G protein-coupled receptors, tiny sensory antennae, on their cell surfaces, it triggers a chain reaction. This chemical whisper ripples through the reef, ensuring that the spawning isn't just a series of random events, but a unified orchestral performance. Notice the texture of the water as we descend slightly beneath the surface. For us, water feels thin and easy to move through, but for a tiny coral larva or planula, the ocean environment is governed by what physicists call a low Reynolds number. Because the larva is only about 1 millimeter long, the water feels as thick and viscous as honey or heavy syrup. Every movement of their thousands of microscopic, hair-like cilia is a calculated effort. This viscosity is actually a benefit. It helps keep the larvae from being swept away too quickly, allowing them to linger in the nutrient-rich snowfall, where their chances of meeting a mate are highest. Picture this microscopic world through the lens of a scientist. Each gamete bundle is a masterpiece of fluid dynamics. The bundles have a density of approximately 0.92 grams per cubic centimeter, while the surrounding tropical seawater has a density of about 1.025 grams per cubic centimeter. This slight difference is the reason the snow falls upward. Each bundle is a tiny organic hot air balloon fueled by high-energy lipids, specifically wax esters and triacylglycerols. These fats provide the buoyancy for the ascent and will later serve as the primary fuel source for the larva during its several-day journey through the open ocean. Consider the thermal stability of the environment. The sea temperature remains a constant, comforting 27 degrees Celsius, or about 81 degrees Fahrenheit. This temperature is vital for the rate of biochemical reactions. Scientists have measured that for every 1 degree Celsius increase in water temperature, the metabolic rate of a developing coral embryo can increase by up to 10%. The reef chooses this specific thermal window in late spring because it is the perfect balance, warm enough to accelerate the growth of the larvae, yet stable enough to avoid the stress of summer heat. You can feel this warmth as a gentle, unwavering pressure against your skin, a thermal blanket that supports the trillions of cellular divisions happening all around you. What is happening now is a transformation of light. While the sun has long since set, the reef is not dark. Many corals are naturally bioluminescent or fluorescent. They contain specialized green fluorescent proteins, or GFPs. Scientists believe these proteins serve several purposes. They act as a biological sunscreen during the day, but at night, they may help attract the symbiotic algae that the new coral polyps will eventually need to survive. As you drift, you might see a faint, ghostly glow of neon green or deep orange emanating from the coral tissues below, a silent neon signal in the deep. At this very moment, the reef's soundscape is at its peak. If you were to listen with a hydrophone, an underwater microphone, you would hear a frequency range of 2 to 20 kilohertz. This is the voice of the reef. Much of this sound is generated by snapping shrimp, which possess a specialized claw that closes so fast it creates a cavitation bubble. When this bubble collapses, it produces a sound pulse of up to 200 decibels for a fraction of a microsecond. This constant crackle, combined with the low-frequency thrum of larger fish, creates an acoustic map. Scientists have proven that coral larvae have a hearing mechanism. They use the direction of these sounds to navigate toward the best settling sites. Deep within the structure of the reef, another silent process is occurring: the regulation of the pH. To build their skeletons, corals must create a localized environment with a high aragonite saturation state. They do this by pumping hydrogen ions out of their internal calcifying fluid, making it more alkaline. This allows calcium and carbonate ions to bond together more easily into the solid stone of the reef. Think of each polyp as a tiny chemical factory, precisely controlling the acidity of the water to weave minerals into a permanent skeletal home. It is a slow, methodical alchemy that has been perfecting itself for 500 million years. Notice how the scent of the sea has changed. This is due to the release of dimethylsulfonopropionate, or DMSP. This is a sulfur-based compound produced by both the corals and their symbiotic algae. It is highly concentrated during a mass spawning event. For marine biologists, this earthy, sweet scent is the first sign that the spawning has begun. For the larvae, this chemical acts as a homing beacon. It is the scent of a healthy, productive ecosystem, a signal that they have found a place where the nutrient cycle is strong. What's fascinating is the choinosarc. This is the thin layer of living tissue that connects one coral polyp to its neighbors in a colony. Through the choinosarc, polyps can share nutrients and even nerve impulses. This means that a coral colony is not just a collection of individuals, but a single, integrated superorganism. When the moon triggers the spawning, the signal travels through this living carpet, ensuring that every polyp on a 3-meter-wide brain coral releases its gametes at the exact same second. It is a level of cooperation that is almost unparalleled in the animal kingdom. As the night progresses, the embryos enter the gastrula stage. Within about 12 to 15 hours of fertilization, the ball of cells begins to indent, forming the first rudimentary stomach and mouth. Even at this stage, they are incredibly sensitive to their environment. They possess specialized cells called nematocysts, the same stinging cells found in jellyfish. But at this larval stage, they are used primarily for sensing the texture of the rocks they will eventually land on. To a larva, a rock is not just a rock. It is a landscape of microscopic textures, and they are looking for a surface that is just right. Picture the reef as a biological loom. It is weaving together the energy of the sun, stored in the algae, the minerals of the earth, dissolved in the water, and the rhythms of the moon to create the largest living structure on our planet. You are floating in the middle of this loom. The underwater snowfall is the thread. Every rising bundle is a new strand of life being added to the fabric of the ocean. This process is so efficient that despite the vastness of the spawning, the reef leaves behind almost no waste. Anything that isn't fertilized is quickly absorbed back into the food web, fueling the growth of countless other species. Scientists discovered that some coral larvae can actually detect the shadow of a reef. Using their simple photoreceptors, they can distinguish between the bright, open water and the dark, sheltered crevices of the limestone. This helps them find a safe place to settle, away from the strong currents of the open sea. It is a primitive form of vision, a way of seeing through the darkness of the ocean floor. As you experience this liquid world, notice the absolute lack of urgency. The coral doesn't rush its growth. The planula doesn't fight the current. It uses the water's viscosity to its advantage. Everything is governed by the steady, unhurried laws of nature. This is the pace of the reef, a slow, patient accumulation of life, mineral, and time. Feel the weightlessness of your own body as it mirrors this patience. You are suspended in a world where time is measured in centuries and growth is measured in millimeters. The water around you is a cradle of chemistry and light. The cryptochromes have done their work. The pheromones have spoken. The lipids are providing the fuel. The reef is in a state of high-energy renewal, yet the atmosphere is one of profound, liquid silence. The only sound is the distant, rhythmic crackle of the shrimp, a sound that serves as the heartbeat of this underwater metropolis. In this deep, scientific wonder, You are witnessing the very mechanics of life, a process that is as complex as a symphony and as simple as a falling snowflake. The reef is working, the sea is breathing, and the future of the ocean is rising quietly toward the stars. As the final hours of the spawning event conclude, the once crowded water column begins to clear, and the billions of newly formed embryos transition into the next stage of their life cycle. The process that follows is a slow, methodical journey from the surface back down to the sanctuary of the seafloor. What is scientifically documented is that within a few days, these embryos develop into planulae, tiny pear-shaped larvae. Each one is equipped with approximately 20,000 microscopic hair-like cilia that beat in a rhythmic wave, allowing them to swim at a speed of about 1 millimeter per second. While they are still influenced by the massive currents of the coral sea, they are no longer just drifting, they are searching. Consider the sequence of their descent. Research shows that coral larvae are initially positively phototactic, meaning they are drawn toward the light of the surface. However, as they mature, their internal biology shifts to become negatively phototactic. They begin to seek the deeper, cooler shadows of the reef. This transition is not sudden, but a gradual settling, much like the way your own consciousness begins to descend from the activity of the day into the quiet depths of the night. The water temperature around them remains a steady, supportive 27 degrees Celsius, providing the exact thermal energy needed for their metabolic restoration and the rapid division of their cells. As the larvae reach the seafloor, they perform a step-by-step exploration of the substrate. They use a specialized sensory organ at their forward end to taste the rock, looking for the specific chemical cues of crustose coralline algae. Scientists have identified a specific peptide, known as GLW amide, which triggers the most radical transformation in the coral's life: metamorphosis. At this very moment, envision a larva finding its permanent home. Within a window of 8 to 24 hours, the pear-shaped swimmer flattens itself into a thin, circular disc. It is anchoring itself for a journey that could last centuries. Once anchored, the coral polyp begins the intricate work of calcification. It secretes a microscopic basal plate of aragonite, a crystalline form of calcium carbonate, with a specific gravity of approximately 2.93 grams per cubic centimeter. This is the foundation of the skeleton. Above this plate, the polyp begins to build the calyx, a stone cup with walls called theca. What is fascinating is the geometry of this growth. Most hard corals belong to the subclass Hexacoralia, meaning their internal structures and tentacles always develop in multiples of 6. You can picture this first tiny polyp, no larger than a grain of sand, extending its first 6 translucent tentacles into the water to begin its life as a colonial architect. The process of building a reef is one of the most patient acts in the natural world. A branching acropora. Coral might grow at a rate of 12 centimeters per year, while a massive porites colony adds only about 3 to 5 millimeters of height in the same 12-month period. This is a timescale that mirrors the slow, steady rhythm of your own breathing. Each millimeter of growth represents thousands of hours of quiet labor, pulling minerals from the seawater and turning them into stone. The Great Barrier Reef, in its current form, has been building itself for approximately 8,000 years, since the last rise in sea level. It is a structure made of trillions of these individual success stories, each one starting with a single night of spawning. Notice the way the nutrient cycle begins to stabilize as the night ends. The sea sawdust and excess organic material from the spawning are not wasted. They are absorbed by the reef's biological pump. The corals produce a thick, nutrient-rich mucus that acts as a reef-wide web, trapping organic particles and recycling nitrogen and phosphorus. This efficiency is what allows the reef to thrive in the nutrient-poor waters of the tropics. It is a closed-loop system where everything is repurposed for growth. Deep within the tissues of the new polyps, the symbiosis with Symbiodiniaceae algae begins. These algae can reach densities of over 1 million cells per square centimeter of coral tissue, providing up to 90% of the coral's nutritional requirements through the conversion of sunlight into energy. As the lunar cycle moves toward its conclusion and the moon sinks lower on the horizon, the reef enters a period of quiet consolidation. The intense energy of the spawning is replaced by the slow, persistent work of development. The water around you is cooling slightly as the early morning approaches, a soft thermal shift that signals the end of the event. The high-frequency crackle of the snapping shrimp remains a constant rhythmic backdrop, but the activity of the larger fish has settled into a nocturnal stillness. What's happening now is a return to equilibrium. The trillions of new lives are beginning their long-term growth, and the parent colonies are entering a phase of metabolic recovery. The heavy lifting of the year is done. The reef is now a sanctuary of potential, a landscape of tiny, microscopic cities beginning to rise from the dust. This sense of completion is also happening within you. The activity of your day has been released, much like the coral gametes were released into the tide, and now you are in the phase of settlement and rest. As we bring our observation of the underwater snowfall to a gentle halt, notice the stillness of the ocean floor. The sand is white and cool, composed of ground-up limestone and the shells of microscopic foraminifera. The water is clear, the currents have softened, and the light of the stars is reflected in the mirror-like surface above. The reef has done its work. It has ensured its future through the same patient, rhythmic processes that have governed the oceans for 500 million years. There is nothing left to do but exist in this space of quiet growth. The rhythm of the tide is the rhythm of your breath. The slow accumulation of the reef is the slow deepening of your rest. Just as the coral polyp retracts into its protective calyx for the night, you are withdrawing into the safety and warmth of your own bed. The world outside continues its ancient cycles, but here, in this liquid twilight, everything is still. The minerals are settling, the larvae are anchoring, and the ocean is a vast cradling weight. Surrender now to the gravity of your rest. Allow the details of the reef, the peach-colored bundles, the pink algae, the translucent tentacles, and the limestone cathedrals to blur into a soft, hazy memory. The science of the sea is a science of patience, and you have all the time in the world. The reef will be there when the sun rises, and it will be there for 1,000 years more. For now, there is only the quiet, the warmth, and the steady pulse-like surge of the sea. I am sinking into a state of total rest. I am supported by the steady rhythms of the natural world. My body is as still and strong as the ancient boulder coral. My breathing is as calm as the neap tide. Every cell in my body is performing the work of renewal. I am weightless, drifting in a sea of peaceful potential. Like the coral, I am anchored in safety and warmth. The energy of the day has been released into the current. I am part of the long, patient history of the earth. My mind is clear and quiet, like the tropical sea at midnight. I am surrendered to the gravity of sleep. I am at peace with the slow pace of nature. My rest is deep, productive, and restorative. The silence of the reef is my silence. I am exactly where I need to be. I am protected, I am calm, and I am still. The stars above the water are the only light I need. I am moving into a long, dreamless sleep. The ocean is breathing for me. The reef is growing in silence. I am resting in the heart of the world. I am at home in the quiet. Good night.